First of all, I would like to thank the organizer for the honor and pleasure to be invited on this remarkable meeting dedicated to Anatoly Moiseyevich Vershik, Toля, as he was for most of us. I can repeat many words that were said by previous speakers, that my field is not close, rather far from Toля, but nevertheless I knew him since far 60s when we were young, just met in one of the first school in Soviet Union in Uzbekistan. There was Sinai, Anosov, Kirillov, I know many people, and we were just new just after the university, entering in that field, and we became close quite fast, and since then used to come in various places, in various circumstances, but there was a lot of things to discuss. First of all, of course, science, especially since the 90s, when he became interested in random matrices related to combinatorics. But to say that he was a remarkable mathematician is a kind of common statement, especially in this audience. But I would like just say that he was enormous human dimension, which is not as common as one would like to have in our community. He was a bright person, being a remarkable mathematician, and all of us, we knew that. So this is important was for me also, the links, historical link between, oh my God. So this last time when I saw Toля, it was in Bielefeld in the beginning of 2010, and there was an interesting meeting, and again we had a lot of things to discuss, both during the meeting, and we live just nearby in Sif. So it's quite hard to make in words the impression and atmosphere in which we were with him. Anyway, so he was a remarkable person and a very good mathematician, and I believe that it is what one has to say. So my talk is random matrices. It is a field in which I am for many years, and I remember when I was in Paris, Vershik used to come rather often, and we discussed by hours and hours various aspects of the theory. But this topic which I am going to discuss, it's a bit far from the Tolya's, but nevertheless I believe that each of us is going to express his own admiration in its own way. My way is just to show that the things at the beginning of which he was still are in good shape and prospering. Well, this is the title of my talk, and this is Toля, and next is just the outline. So the talk is related to, I have to say, to a bit fashionable things now. It's called entanglement. It is fashionable because of the perspective of quantum computers, which is quite vague in my opinion, but it stimulated just an explosion of research around. Well, and this is the outline of my talk. Well, this is a definition of entanglement, which, by the way, was formulated in a bit negative sense by Einstein in 1935. He was invented this notion. He revealed this property of quantum mechanics, just trying to prove that quantum mechanics is not complete theory. And then immediately the same year, Schrödinger understood the positive, quite important meaning and the essence of the phenomenon. And the definition is very simple, but before to this definition, let me give a couple of definitions from mathematical frameworks of quantum mechanics. So we have, in quantum mechanics, we describe the system by the state. The state is just, oh my God. So the state in quantum mechanics is just the positive definite matrix of trace 1. It's a quantum analog of probability distribution. And we say that the state is pure if this density of states rho is just a rank 1 projection. Then we have another definition that in many cases you see your system as a consisting of two parts. In that case, because we have a bipartite system. And this just means nothing mathematically, is that we would like to write our state space of our system just a tensor product. Well, and then we say that this is a main definition. We say that the state is entanglement if it is not a product. In probability terms, it's just if your two random variables are dependent. So the probability density doesn't factorize. So it's very simple, but turns out that quite deep and had many things. Well, and next, this is an example, very simple example. It took 30 years, by the way, to invent this example. It was invented in the 60s, a typical example of the entanglement state, because it's a sum of two, so it is not a tensor product. And if your state, our state is not pure, that means that the density matrix rho is not just rank 1 projection. Then the definition a bit more complex, but we will not use it just for completeness. Well, yes. We have to introduce the important quantity, which, okay, has tens of definitions and uses, but I just would like to discuss the one related to quantum mechanics called von Neumann entropy. It is just the non-negative number defined by that formula. And if we immediately recognize that if our density matrix is just a pure state, then the entropy is 0. And if we compute what is the maximum of entropy with respect to all possible positive definite operators of rank 1, we'll find that the maximum is log 2 of n, and the corresponding density matrix, just the unity normalized, just unit operator normalized to trace 1. And this gives the motivation to view the entropy as a measure of, there is a jargon called quantifier of entanglement. So depending, the more is entropy, the more entanglement we have. Von Neumann entropy. Yes. Then we need the next definition. If you have our bipartite system, but we are interested only in one part of them, say A, we make a trace with respect to the second. This is why we present our space as a tensor product to define this partial trace. And it is analog, quantum mechanical analog of marginals in probability. Yes. And then if you take this reduced density matrix and compute the entropy, so it will be it's called entanglement entropy. It is the main subject of my talk and one of the main quantifiers, the others in the field. Yeah. Again, I just repeat: if you take the pure state, the Bell state that I mentioned before, and then I trace out the degrees of freedom of B, to have only degrees of freedom of A, so the state of the part of my big system will be maximally entanglement, despite that the initial state of the whole system was pure. So it is just a good illustration that the entropy is a good entanglement quantifier. So we are going to discuss it. And what is the problem? There are many problems in the field, but a considerable part of the field has the following setting. You have a big system, and you have a certain, which lives in the space, in the real space, lattice, or here is a lattice, it could be Rn, Rd, And then in our subsystem, which we are interested in, it's just a part of that. We call it block now. And I assume that the sizes of these two, the whole system is n, and the sizes of size of subsystem is L. And I would like to study this asymptotic regime when the system is very big. Block is also big, but less than all the system. And I would like to study, this is just heuristics, this inequality, but the mathematical implementation, just you do the limit omega to infinity, the standard things in statistical mechanics called macroscopic limit. And then we are left with the entanglement entropy of the block, which lives inside of infinite system. And now we would like to see what is going on if the block is, the size of block is growing. And the field is very remarkable beginning, because it was discussed in the 70s in the context of black holes. It is still quite alive. Then there were people doing it in quantum field theory, and eventually in mathematical physics. This is Kardikor-Repin. And they found that if you have this setting, the block of the infinite quantum system in the block, and you would like to see what is going in this block growing. So the asymptotics like that it could be either just the area of the surface area of our block, and then we say that it's area law. It's good tradition coming from probabilities that if you have something, even not so deep statement, we call it law. So here we use the same tradition. We say that it's area law, and sometimes you have a additional factor log, which depend on the physical property of the system, which I will not discuss here. And so most of the results, they are about rigorous result. After all, we are doing certain mathematical physics. So most of the results, these are for one-dimensional cases. And the multi-dimensional cases, they are mostly heuristic, numeric, and there is basically only one system or model, whatever you would like, in which it could be done rigorously. It's called free fermions. I'll explain on the next slide what is it. And sometimes you have the situation when your entropy is proportional to the volume, but it is standard situation which dates back to the founding fathers of statistical mechanics, even classical. In quantum case, it is also known. Well, now I am explaining what are free fermions. Mathematically, it's just our state space is multidimensional space, but of anti-symmetric functions, and we have a self-adjoint operator, because quantum mechanics is not only states, but of course these are interaction in the state, and the phase of the state it's Hamiltonian. But Hamiltonian in that multi-dimensional space is rather simple. You see, it is just acting on each term of the product. And this is why we say that are free fermions, because if fermions are not free, then the Hamiltonian will be much more complex. Well, and I need to know this definition. I need to know two numbers. One of them called Fermi energy, second called temperature. And then you see where they... And I need three more simple definitions. The first is a function written in the first line. It's called Fermi distribution. Then it is standard definition of linear algebra. If you have a large matrix operator, differential operator acting in the whole space, and you just would like to take the block of matrix, or just restrict your operator on the finite volume, we call it restriction. And I need this function, which is, it doesn't relate it to the talk, but it is known as a binary Schonen entropy. And then having these things, I can define, I can calculate by using the technique of second quantization, what is my entropy. So I repeat, we are in a big volume omega, which is going to be infinite at the moment. we take a block living in the domain lambda, then what do? We take our Hamiltonian, it's called one body. Let me recall. One body, there is no. Oh, very good. So this is one body, because it acts only on every particle. We have omega particles, but it acts only, there is no interaction between particles. Well, and then by using that, this is a formula which makes all the part of the theory living. My God. Well, and this is entropy. So we have a formula which in fact was known long before, but explicitly proposed by Ingo Pesce. And the formula just allows you to compute the entropy. So you take your one body Hamiltonian, which determine your quantum system. Yes. Then you make it. This operator lives in the whole space. Now you restrict it to your block. You compute the function of that self-adjoint operator, and then you put insert of the Shannon entropy. So you have a formula which make links with the mathematical physics, theoretical physics, with spectral theory, because especially if you are at zero temperature, there is a temperature here. So let me go a bit back to see. You see, this is Fermi function, but we are interested mostly in the zero temperature. Okay. After all, I'm from the Institute of Low Temperature Physics. Yes. So if you take temperature zero, so this function is just the characteristic function of semi-axis, and this is most interesting case in certain sense. And now, if you take this zero temperature case, you arrive to the formula with t equals 0. It is a formula. You see, you take things which is called Fermi projection, but in fact, for those who knows spectral theory, it's just the resolution of identity of your self-adjoint operator. So you have a link to the spectral theory with a lot of technique and results of the theory. But the formula looks simple, but in fact it is not a simple story, because again, for those who heard about spectral theory, we know that the resolution of identity of self-adjoint operator is everything. If you know resolution of identity, you know everything. So in fact, this is on the output of the whole spectral theory, this formula, and this makes it not simple and quite interesting, because there are not so many cases when the spectral theory provides us with the knowledge of this Fermi projection. And the main work is to say something about this Fermi projection. Yes. Well, no, still not working. And let me just say a few words about known results. People started to work in multidimensional case, just translation invariant case. Your system lives in the space which is invariant with respect to translation. In that case, the Hamiltonian is a just convolution operator on the lattice. And I assume that the entries of this matrix, they decay sufficiently fast perpendicular to the principal diagonal, and this is called in physical terms short range. And if you take this situation, so you can prove the things that were found before by physicists in certain models, and quite often not so rigorously, to be frank. And this, in that case, in that model, this is why we like this model. You can do everything rigorously. You have three assertions written here. So you have the area law. In the case when epsilon, the energy, Fermi energy, let me remind you what is a Fermi energy. You see? So your Fermi projection, it is just the projection, the sum of all eigenfunctions whose eigenvalue is below the epsilon Fermis. Yes, and then you do this and you get, so if you are in the gap of the spectrum, now everything in the term of the spectrum. If the Fermi energy is in the gap of the spectrum, you have a real law. If it is inside the spectrum and the spectrum of that operator is absolutely continuous, then you have additional log. And if temperature is bigger than 0, or if the states are not a ground state, your system lives somewhere in excited state, then it will be volume law. And it took quite a lot of time to prove this. First of all, the result for one-dimensional case was obtained by Harold Widom, in my opinion, one of the most remarkable analysts of 20th century. And it was done, by the way, not in the context of quantum mechanics, but in context of signal transmission theory. Then Sasha Sobolev from initially from Leningrad and then from Imperial College of London did multidimensional case. And as for volume law, in that case, it is trivial corollary of well-known result of analysis in spectral theory called Sego's theorem. Well, now, what about the case when your system is not translation invariant, is not ideal? After all, quantum computer, it is made from certain material which is not ideal. There are impurities, there are imperfections. So let's consider the case when our operator is random. And simplest case that the Schrödinger operator is random potential. And in that case, we have again a real law, but not only in the gap when we are in the spectrum, but now the spectrum is pure point. It's called Anderson localization. If you can get even enhanced law, I mean additional log in a very special case, because a lot of people, maybe not in this audience, they know what is the Anderson localization, that the spectrum is pure point, but there are tricks in that pure point spectrum. In some points, isolated points, there are no localization. There is a solution of this corresponding Schrödinger equation which doesn't decay. And this is called transparency energy. And in that case, we get again enhanced real law. So there is a certain correspondence which is not yet formalized between the results of quantum information theory and the spectrum type. And here we see some manifestation. And to get a volume law, you have standard things again, analog of Sego's theorem, but there are certain interesting things in subleading term which I have no time to discuss, and it was done by in the group in which I was a member. Well, and now what is left? You see, from the list that I mentioned, we know more or less what is going on in all cases except one. When we have the long-range hopping, that means your Hamiltonian, its entries decays quite slow. And this case is technically quite hard, not yet done. And as a sum of surrogate, if you want, let's consider as a one-body operator random matrix. Random matrix is, okay, this is defined, it's n by n Hermitian matrix whose probability distribution written in that form. So you have a differential, just the standard Lebesgue measure in the space of Hermitian matrices. And you have a weight, which written here. And if this function v, which could be more or less arbitrary, but if it is a special, it's just a parabola, maybe a lot of people here, they heard that it is called GUE. And in that case, you see that all the entries, they are of the same order. Okay, it depends on n, but it is not a point. A point is that there is no decay of the entries when the difference m minus n grows. And this is why it is a kind of surrogate, by the way, widely used in modern theoretical mathematical physics, of the long-range interaction, which happens quite often. Well, so it's our way to see long-range case. And then what we'll obtain in that case? What we do know, there are two results from random matrix theory written upper part of the slide. First, we compute the standard things, the things from it's in the beginning of any study of spectral theory. You should know the distribution of eigenvalues. In that case, this distribution is known. Okay, it is proven that it exists, and in certain cases could be computed explicitly. For example, for GUE, Gaussian unitary ensemble, it is just it's known as a semicircle law, dates back to Wigner in '52. And then there is important property, in fact, crucial in this talk, that the eigenvectors, eigenvalues, they live quite complicated life, but eigenvectors are quite simple. Eigenvectors of that matrix, because of trace here, you can easily see that the distribution, it is a unitary invariant. If you replace the matrix M by the unitary equivalent case, the distribution is the same. And the corollary of that is that eigenvectors, if you take n eigenvectors of that matrix, they form a basis, but it will be the basis which is random, but it is distributed with uniformly with respect to rotation of the basis, that is a unitary group. So this is very important property that allow us again. Okay, as I said, Fermi projection is quite complicated object, but here it is simple. This is motivation why I chosen this thing. So the Fermi projection is just, you see, just written here. So it is just, okay, I'll write in the next slide. So your Fermi projection is explicitly written. It is again random, of course, since your Hamiltonian, your matrix is random, but it's simple. It has a rather simple structure written here. So this is just a unitary matrix, random unitary matrix, hard distributed with respect over the unitary group, and you write just the bilinear form. And then, since you know the projection, you need not a projection, but its restriction. So I restrict the indices from 1 to n to 1 to L, and it is my P, which I have to input in the formula. And the limit which I am going to take here, quite remarkable. So, of course, n tends to infinity. It is the size of our system. But we have to, in the standard situation, which I showed in the first slide, we do first limit n to infinity. We get the limit, and then we study asymptotic with respect to L. Here it is impossible. You have to do simultaneously, because Hamiltonian depends on n, it doesn't exist when it tends to infinity. So you are obliged to do these things, and it is interesting because it's kind of new asymptotic regime. What do you get? Well, first, as I repeated many times, the Fermi projection is a complicated object. Therefore, as a Pullman story, let's try to find some bounds, not asymptotic, but just bounds. It turns out there's a lower bound and upper bound, and what is remarkable, lower bound is just bilinear with respect to P. So it is more or less simple to calculate, because to calculate the entropy, you have to calculate not the square, not the bilinear form, but the function x log x, highly nonlinear. So, but nevertheless, if you compute this, it's not too hard calculation. I wrote here it is an expectation with respect to unitary group, because I remind you that we are in the situation where our operator is random, its resolution of identity is also random. Therefore, we have to take expectation as the first step. It's good to know things with probability 1, but it is not always possible. Well, but even this Pullman story gives you certain understanding, because you see we have a bounds, but this bound is consistent only with volume law, because I repeat, there are 3 limiting laws. A real law in one-dimensional case just a constant, then enhanced real law, it is additional log, and the volume law, it is just a volume. Here we have one-dimensional volume, that is length, the size of matrix. So we have something hinting quite strongly that the corresponding limiting law in this case will be volume law. Okay, now how to compute it? Well, I introduce now, I remind you that the entanglement entropy is determined, you take the Fermi projection and then its restriction. Now I view it as it is self-adjoint operator, so I introduce the distribution function of that operator, and if I introduce then bispectral theorem, gives me immediately the formula, showing that to find the entropy, we have to just find distribution of eigenvalues in that limit that I showed. Yes, and this is okay, we are coming to the standard problem of random matrix theory. You have a random matrix, you would like to know how do its eigenvalues distributed. Well, in that case, so let me write it in symbolic form, not in the entries. So what do we do? We have our we have our canonical basis in our n-dimensional space. It plays the role of our big volume, our system. I am coming. Yeah, I am finishing. Yes, and then our restriction of our Fermi projection is written here. These are projection on the span. This plays the role of my Fermi system. Here it is a box, our block, and it is a matrix. So random matrix theory knows something even about more general case. You replace PL, pi L and pi K by two positive definite operators. You get this matrix, again with the same U, and you know distribution, eigenvalue distribution of B1 and B2, you would like to find distribution of that complex, yes? So roughly, you would like to determine the binary operation between measures. You have a measure, limiting measure for B1, eigenvalue distribution, limiting measure for V2, and you believe that there is a limiting measure of that, which could be, of course, expressed via limiting measures of these two terms, yes? And so this symbolic operation written here, in random matrix theory we say that it is law of multiplication of random matrices, but there is a more or less new field which called free probability, which came from sister algebra, etc., in which, you also can find this, and they call it multiplicated non-commutative convolution. Well, so we have to, and this problem is more or less partly known, partly not, but just for the purposes that in that work I computed it explicitly, and you see the formula. So our limiting distribution of this Fermi projection, restriction of Fermi projection, you see there are two atoms, and 0 and 1, they are atoms, and there is something in between, so your density of your distribution is like that. 1, 0. There is a peak, there is a peak, and there is certain part here. And the peaks doesn't contribute to the result because the function h, which is written, function h on x is minus x log 2x minus 1 over x log 2 1 minus x. So it is 0 and 0 and 1. So only this part contribute to the entanglement entropy. And we have a asymptotic formula showing that we have indeed the analog of volume law. There is a size of our matrix times certain coefficient which depends only on the parameters of our problem. So we have this formula, and the formula, you see, it is a function of two variables, and you can't write closed expression for this s little s lambda k kappa because there are four different expressions depending on how many atoms you have. 0 atoms, all atoms, or just one of them. But you get some certain surface, and this is the form. So you see, it is our, specific entropy, and you see it is in the middle. So this is a form of that coefficient, and there are bounds from below and from above. They are quite close. So this solves the problem and shows that indeed if you have a long range situation, then indeed the volume law even in zero temperature, you'll get as a result. Well, I believe that it is all. I have one more thing to discuss, but I have no time.
We have time for a few questions.
Thank you very much for the very talk. Just naive question. So you're speaking about free fermions. If it would be free bosons?
No, free boson. No, it could be that the situation is completely different and much less interesting. Yeah, you can.
And another, so you're talking about quantum theory, but if we discuss statistical physics where we have this spins just plus minus one, not three, is there some analogy for the statistical?
Spins themselves, they are quantum. There are no spins in classical theory. But volunteer, you can, but it's hard so far. So this is why a lot of people still working on free fermions, because the only model in which you can proceed more or less, I know, considerably. And this is still quite hard problem, because there is no formula that I wrote in the beginning. In one-dimensional case, you manage, because one-dimensional spin models, many of them, they are explicitly solvable. This is the point. There is beta and that, there is Jordan-Wigner transformation, but it's only one-dimensional case. Yeah, unfortunately. The reason is very simple. We are not able so far.
Tanya.
I wanted to ask you, so you showed some examples of spectral computations, and in some cases it was absolutely pure point spectrum, and then there was an example with two point masses and absolutely continuous spectrum. I wanted to ask, in these situations, are there some natural examples which lead also to the presence of singular continuous measure?
It's a very good problem. We just wrote a grant to study. Yeah, indeed, it's very. You even know. I don't know. I know no person who can predict which formula will appear. Okay, because considerable part of spectral theory deals with eigenvalue, but here you have to deal with eigenvectors, and it is harder work.
Okay, so we can continue discussion during the.
Thank you very much.
Okay,
Yes.
thank you very much.
Mm-hmm.